Hey guys, welcome to this easy maths video. Today we are looking at the Junior Maths Challenge from 2019, questions 11 to 20. Question 11 says two players X and Y take alternate turns in a game starting with the diagram alongside. At each turn, one player writes one of 1, 2 or 3 in an empty circle, so that no two circles connected by an edge contain the same number. A player loses when they cannot go. In each of the 5 diagrams below, it is Y's turn. In each of the diagrams, can Y's move ensure that X loses the game? Okay, so if we look at each of the diagrams below, starting off with diagram A. Okay, so let's say that player Y starts here. Well, the two adjacent circles contain a 2 and a 1. So that means that the only number that we can put in this circle is 3. Okay, so once player 1 has had their turn, it's now player X's go, and player X is going to have to put a number here. And that number has to be a 3, because we've got a 2 here, a 1 here, and a 2 here, and they are all of the adjacent circles to this circle. So this will also be 3. So as we can see, player Y cannot ensure player X will lose. Okay, diagram B. So let's say player Y starts here. So they could either place a 2 or a 3 here, since the only adjacent circle is a 1. So let's say they place a 3 here, then player X would have to play here. Now player X can't play a 1 or they can't play a 3, because obviously 3 is this adjacent circle and 1 is this adjacent circle, so they would have to play a 2. If player Y played a 2 here, then player X would have to play a 3 here. So either way, player Y cannot ensure that player X will lose for diagram B. Diagram C. So again, if player Y starts here, they could either put a 2 or 3 here. So let's say they put a 3 here. Then player X can end up putting a 1 or a 2 here. So let's say they place a 1 here. And again, you could also have 2 here. And then again, player X can still play a 1 there. So again, there are no examples where player 1 will ensure that player X loses the game for diagram C. So diagram D. So player Y can go here. So say they play a 1, then that would mean that player X would have to play a 3 here. But let's say instead that player Y plays the 3 here. Now there's a bit of a problem, because player X has to play here, and if we look at the adjacent circles, we've got 3 here, 1 here, and 2 here. Therefore, it can't use any of the numbers 1, 2, or 3. So D must be the situation where X loses the game. So let's just check diagram E. So again, player Y could start here, they could play a 2 here, player X would have to place a 3 here, player Y could also play a 1 here, but then again, player X could play a 3 here. So player X won't lose in that diagram. So our final answer must be D. Question 12 says Jamil writes down a sequence of 6 integers. The rule he uses is after the first 3 terms, each term is the sum of the 3 previous terms. There is his sequence, and we need to figure out what the first term of that sequence is. So if we replace the blank spaces with letters, and we're going to call those letters A, B, and C to keep it simple. So we've got A, B, C, 8, 13, 25. Now the rule states that after the first 3 terms, each term is the sum of the previous 3 terms. So this is the first term that we actually have a value for, which is A, and the previous 3 terms are A, B, and C. So that means that we can form an equation here which says that A plus B plus C equals 8. Then if we look at the next term, which is 13, that's going to be the sum of the 3 previous terms, which is B plus C plus 8 equals 13. Lastly, we've got 25. So the 3 previous terms are C plus 8 plus 13 equals 25. As you can see here, we've got 3 equations. And the third equation we can easily simplify, because we just have one unknown, which is c. So 8 plus 13 is 21. So we're going to have c plus 21 equals 25. And then if we subtract 21 from both sides, we're going to get c equals 4. Okay, so then we can substitute this value of c into equation 2. So then we're going to have b plus, so c is 4, so it's plus 4 plus 8 equals 13. This becomes b, and then 4 plus 8 is 12 equals 13. And if we subtract 12 from both sides, we get b equals 1. Now we've got a value for b, so then we can just substitute our values for b and c into equation 1. And then we can work out our value for a, and a is the first term in our sequence. That means we're going to have a plus b, which is 1, plus c, which is 4, and that's equal to 8. That simplifies to a plus 5 equals 8, and then we can subtract 5 from both sides, so we get a equals 8 minus 5, which is 3. So 3 is the first term in our sequence, and that is answer D. Question 13 says, in how many different ways can you spell out JMC, starting at the centre and moving to the next letter in a neighbouring square, horizontally, vertically or diagonally each time? Okay, so the question says that we can move to the next letter horizontally, vertically or diagonally. Right, so let's think about what happens in the first scenario when we move horizontally. Well, we've always got to start with J, as there's only one J on the grid. Horizontally, we can either go in the left direction or the right direction. So let's say we go right first, then we're going to end up with this M here. And then from this M, you should be able to see that, yes, there's a C here, but there's also a C here, and we can move to those other two C's since we are able to move diagonally. So in this case, there are 3 possible ways in which we can spell JMC. So that's when we go in the right direction. So the same is going to happen when we go in the left direction. And you'll see here that we end up with the exact same number of ways that we can spell JMC. It's 3. So in this case, in the horizontal direction, we can just say that 3 times 2 equals 6. So there's 6 ways of spelling JMC in the horizontal direction. Okay, so let's do the same vertically. Okay, so vertically we can either go up or down. So if I just get rid of this, then we always need to start off with J. So say we're going up. So this will be our letter M. And then of course we can choose this value of C, but then we can also choose this value of C and this value of C, since we are able to go diagonally. So again, there are 3 ways in which we can spell JMC, and then we can do the exact same, but going down. So we're going to have this value of M, this value of C, this value of C, and this value of C. So again, we're going to have 3 times 2, which equals 6. So there's 6 ways of spelling JMC in the vertical direction. Now the last way is a little bit different. So this is diagonally. So when we go diagonally, instead of only having 2 possible options, so when we went horizontally we had a left and a right direction, and when we went vertically we could either go up or down. Well, when we go diagonally we're looking at all the corners, so we're looking at this value of M, this value of M, this value of M, and this value of M. Okay, and from each value of M, how many C's can we get to? From this M here, we can go to this value of C, this value of C, this value of C, this value of C, and this value of C, since we can move both horizontally, vertically, and diagonally. And we can move to 5 values of C for every value of M. So there's 4 values of M, and there's 5 C values, then we're going to have 4 times 5 is 20. So therefore, in order to work out how many different ways we can spell JMC, we just need to add the number of ways we can spell it horizontally, vertically, and diagonally. So that's going to be 20 plus 6 plus 6. So we're going to have 20 plus 6 is 26. 26 plus 6 is 32. And we've got an answer of 32, which is answer E. Question 14. Each edge in the diagram has length 1 centimetre. What is the length of the longest path that can be followed along the edges, starting at a vertex and without revisiting any vertex? Okay, so for this question, we want to find a vertex which is further away from any other vertex. So one possible option would be starting from this vertex here, and then somehow getting to one of the vertices on this triangle. So if we start at that vertex, we want to go in this direction, and then to get to the triangle, we don't want to go this way, because that's going to make the path very short, so instead we can go this way. Now, we can't go left, because if we go left, then we've got to end up coming back on ourselves. So we could go down here instead, then across here, then here, then here. And now, to get to the triangle, it doesn't really matter what direction I take. I can either go up here and down here, or I could go along here and up here. Either way, the number of edges is still going to be the same. So the number of highlighted edges that I've got here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each edge has a length of 1 centimetre, so therefore the length of the total path is 10 centimetres. So that is answer D. Question 15 says all 4 L shapes shown in the diagram are to be placed in the 4x4 grid so that all 16 cells are covered and there is no overlap. Each piece can be rotated or reflected before being placed, and the black dot is visible from both sides. How many of the 16 cells of the grid could contain the black dot? Okay, so what we're going to do is we're going to take each of these 4 L shapes. We're going to see all of the different ways in which we can place them in the grid, and then we're going to try and figure out what cells the black dot will end up covering. Okay, so let's start off with a fairly basic example. So we could have an L shape here. We could have one that's then rotated so it fits here, and then we could copy this exact same process here. So let's say, for instance, that the black dot is here, then of course this cell will contain the black dot, but then of course any of the L shapes could contain the black dot. So the black dot could also be here, could be here, and it could be here. So that means it covers this cell, and this cell. Let's have a look at another example. So we could have an L like this, an L like this, an L like this, and an L like this. Okay, so for this first L shape, the black dot is already in its correct place, so we don't need to highlight anything for that. But we could also have a black dot here, so that means it covers this cell. There would also be a black dot here, which covers this cell, and there would also be a black dot here, which covers this cell. Okay, so if we look at another example, so we could have an L here, an L here, an L here, and an L here like that. So in this example, the only difference is this cell here, which we can highlight. Now we could also place an L here, 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 and here, which means that this space would be covered, this space would be covered, and this space would be covered. We could also try and fit an L here, 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 and here. So in this case, we would have the black dot here, we would have the black dot here, we have the black dot here, we would have the black dot here. So that would cover all of these 4 spaces here. So the only space which is not covered is this space here. So now we just need to think of an example of where we can place an L shape with a black dot so that the black dot ends up in this last grid space. So we could have an L like this, and we can place another one like this, and then we could just do the exact same. It doesn't really matter where we place the other two L's. So that means that we would end up with a black dot here. So therefore we've shown that no matter whether we rotate or reflect these L shapes, the black dot will end up covering every cell within this 4x4 grid. And of course there's 16 cells on this grid, so the final answer must be E. Question 16. Tamsin writes down the 2-digit integers. One is square, one is prime, and one is triangular. She uses the digits 3, 4, 5, 6, 7, and 8 exactly once each. Which prime does she write? Okay, so we're looking at square numbers, prime numbers, and triangular numbers. If we work out what the square numbers and triangular numbers could be, then we should be able to figure out, using the numbers that are left over, what the prime number is going to be. Okay, so we know the square numbers, which are 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. And of course, the question says that the only digits that are used are 3, 4, 5, 6, 7, and 8. So that excludes all of these numbers. So the only square numbers we could possibly have are 36 and 64. Okay, what about the triangular numbers? Well, the triangular numbers, the way to remember them is by drawing some dots. Okay, so they look like this. So essentially it's going to be 1, 3, 6, 10. So basically the way triangular numbers work is we add 1 to the difference each time. So the difference here is 2, the difference here is 3, the difference here is 4. So next difference is going to be 5, which is 15. Then 6, which is 21, then 7, which is 28, then 8, which is 36, then 9, which is 45, I'll write it here, and 10, which is 55, then 11, which is 66, then 12, which is 78, and that is as high as we'll go to. So what numbers can we exclude? Well, it's 2 digits, so we can exclude these numbers. We can exclude the 1 and the 0 because we don't have those numbers. We don't have a 1, don't have a 2 or 1, don't have a 2. 36 we can include. 45 we can also include. 55, now it says that each digit is only used exactly once. So we can't have 55, neither could we have 66. So the only triangular numbers we can have is 36, 45, or 78. Okay, so if 36 is the triangular number, then that means we've already used up the 6, which means that we couldn't have 36 or 64 as one of our square numbers. So 36 can't be a triangular number. Okay, let's say that 36 is the square number and 45 is the triangular number. So in that case, we're going to be left with 7 and 8 left over. Well, 78 is not prime because it's even. And 87 is not one of our options. So it can't be that. What if 36 is a square number and 78 is a triangular number? Well, in that case, we're left with 4 and 5. 45 is not prime because it ends in a 5, and 54 is not prime because it's even. So that doesn't work. So the other options we've got is 64 and 45. We can't use that because we would be using the 4 twice. So our only other option is using 64 and 78. So if we use 64 and 78, we're going to have 5 and 3 left over. 35 is not prime because it ends in a 5. 53 is prime and it's one of our options, and it's the last 2 pair of numbers that we haven't checked. So our answer must be C, which is 53. Question 17, a rectangle is 3 times as long as it is high. The area of a square is 12 times the area of the rectangle. What is the ratio of the perimeter of the square to the perimeter of the rectangle? Okay, so we're going to have a rectangle. Let's say it looks something like this. Okay, and we can call this x. And if it's 3 times long as its height, this is going to be 3x. And then we're also going to have some square, right, where the area of this square is 12 times the area of the rectangle. Now, and obviously the square is going to have the same side lengths, so we could call those side lengths y. Okay, so the area of the rectangle is just 3x times x, which is 3x squared. And the area of the square is 12 times the area of the rectangle. So that's 12 times 3x squared. 12 times 3 is 36, so we get 36x squared. Okay, and we need to find the ratio of the perimeter of the square to the perimeter of the rectangle. Well, I said that my side lengths are y, so the area of the square is going to be y squared, so we can say that y squared equals 36x squared. Then we can take the square root of both sides and we get y equals plus or minus 6x. Now, and obviously we're looking at lengths here, so we're only going to take the positive square root. So we're just going to get y equals 6x for each of the sides. So now we can work out what the perimeter of the rectangle and the square is in terms of x. So the perimeter of the rectangle will be 3x plus 3x plus x plus x, which is 8x. And then the perimeter of the square will be 6x times 4, which is 24x. And then we're working out the perimeter of the square to the perimeter of the rectangle, so that's 24x to 8x. We can then divide through by x, so that the x's cancel out. So then we're left with 24 to 8. And then we can divide through by 8, so we get 3 to 1. And 3 to 1 is answer D. Question 18 says, what fraction of the integers from 1 to 8,000 inclusive are cubes? Okay, so we need to think of all the cube numbers from 1 that go up to 8,000. Okay, so let's say that cube number is represented by x cubed. So we're saying that x cubed has to be between 1 and 8,000. So if we write down some of our cube numbers, so we know that 1 cubed is 1, we know 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. So we're looking for some number that when we cube it, it's less than or equal to 8,000. What happens if x cubed is equal to 8,000? Then all we've got to do is take the cube root of 8,000. So you cube root both sides and you get x equals the cube root of 8,000. Well, I can split this cube root up. I can rewrite it as the cube root of 8 times the cube root of 1,000. And I know what these values are because I know that 2 cubed is 8, so the cube root of 8 is going to be 2. And then the cube root of 1,000 is just 10, because 10 times 10 is 100, and 100 times 10 is 1,000. So that's just 10. So then I'm just left with an x value of 20. So that means that there's 20 cube numbers up to 8,000, exactly 8,000, because 20 cubed is 8,000. That's what we've just shown here. And if we're working out the fraction of the cubes out of the total number of integers up to 8,000, then the total number of cubes is 20, and the total number of integers up to 8,000 is 8,000. So it's 20 over 8,000, and then we can just divide the numerator and the denominator of this fraction by 20. So 20 divided by 20 is just 1. And then 8,000 divided by 20 is 400. So we're going to get 1 over 400. And we've got an answer for that, which is C. So our final answer is C. Question 19 says each row, each column, and each of the bold 2x3 rectangles in the grid has to contain each of the numbers 1, 2, 3, 4, 5, and 6. One number in each cell. What numbers should go in the cell marked X? Okay, so X is here. This is the number we're trying to figure out. So this is basically just a Sudoku question. So let's go through each of the numbers one by one. So we'll start off with X. Could X be 1? Well, X is in this column here. And in this column, 1 cannot go here because there's a 1 already here. Okay, now could a 1 go here? It could do, because we need a 1 within this 2x3 grid, and we've got a 1 here, so the 1 can't go here. So yeah, we could potentially have a 1 in this cell here. But we could also have a 1 in X, so I'm going to put a 1 just above X, just to mark that as a possibility. So there are 2 options for 1. What about 2? Well, again, 2 can't go here, because we've got a 2 here, in this row. 2 can't go here or here because we've got a 2 here within this grid. Right, well, every column needs to have every number from 1 to 6. So we have to have a 2 somewhere here. Well, the only other option we could have is where X is. So the 2 would have to go here. That's the only option. So that makes me think that my answer is 2. Okay, so in this case, if we did have to figure out more of the puzzle, that would mean that this cell would have to be equal to 1. What about 3? Well, it can't be 3 because we've got 3 in this column anyway, so we can definitely get rid of 3. Same with 6, since we've got a 6 in this column here, so I can get rid of 6. So the other one we haven't checked is 4. Now 5 isn't even an answer, so I'm not going to consider that. Well, based on this, 4 would have to go where this X is, because there's already a 4 here, which means that it can't go in this cell here. And then this missing X here would be a 5. So the X that we're looking for has to be 2. So our answer is B, which is 2. Question 20. Emily writes down the largest 2-digit prime such that each of its digits is prime. Krish writes down the smallest 2-digit prime such that each of its digits is prime. Kirsten subtracts Krish's number from Emily's number. What answer does Kirsten obtain? Okay, so it's a 2-digit number. So the largest possible 2-digit number would be 99. Okay, well, all the numbers in the 90s don't include a prime digit since 9 is not prime. Okay, so what about the 80s? Well, again, 8 is not a prime number, so it can't be any of the numbers from the 80s. 70. 7 is a prime number. So we start with the largest number from the 70s, which is 79. And 7 is a prime number, but 9 isn't, so that can't be right. 78. 78 is even, so that's not prime. 77. Well, 77 is divisible by both 7 and 11, so that's not prime. 76 is even, so that's not prime. 75 ends in a 5, so that's not prime. Again, 74 is even, so that's not prime. 73, it's not even. It doesn't end in a 5. It's not a multiple of 3. It's not divisible by 7. So it looks like 73 is prime. Okay, so we can say that 73 is the largest possible prime number that we can have, where both the digits 7 and 3 are prime. Now we need to find the smallest possible prime number. Okay, so obviously it can't start with a 0 because that's not a 2-digit number. Can't start on a 1 because 1 isn't a prime number. So the smallest numbers would be the 20s. So 21. Well, again, 1 isn't a prime number, so we can't have that. 22. 22 is even. We can't have that. 23. 23, again, it's odd. It doesn't end in a 5. The sum of its digits is not a multiple of 3. And it's not divisible by 7. So 23 must also be a prime. So 73 is the largest prime, 23 is the smallest prime, so the difference is just going to be 73 minus 23, which is 50, and that is answer E.